So to show my appreciation of hitting 2,000 followers, I'd set up a poll to allow you to vote on which meter you'd like to see run next. And of course everybody wanted to see the new EEV blog 121GW. And unfortunately, of course, that meter is not yet released to the public. But the next meter on the list was a Gossen Metrawatt. So to give you an idea kind of what I'm looking for feature-wise, these are the 4 meters that I basically would rank the highest feature-wise. Starting on the left, this is the SEM DT9939. The cost on this meter is about $120 US. This meter is rated for Cat 4 600 volts. It's 40,000 counts. It has a single temperature input, but it is a tri-display. The real nice thing about this meter is its wireless interface. This meter can resolve down to 10 microvolts DC. To the right of that, I have my favorite meter. This is the Bryman BM869S. This meter cost about $230 US. It's Cat 4 1000 volts rated. This meter has a resolution of 50,000 counts, or you can select the high res mode where it has a resolution of 500,000 counts. The nice thing about this meter has 2 temperature inputs. The downside is this meter did not come with an interface cable. You had to actually pay extra for that, and I think that was like a $50 option. This meter can resolve down to 1 microvolts DC. Next we have the Unity UT181A. This meter costs about $300. It's Cat 4 600 volts rated. It's a 60,000 count meter. It also has 2 temperature inputs. It's a graphing meter, so you can log data and graph it. It came with the IR interface in the software. This meter can also resolve down to 1 microvolts DC. And to the right of that I have the Greenline Meter. This was made by Summit and it's rebranded by TPI. It's the TPI 194-2, and this meter has a price of $250. It's also Cat 4 600 volt rated, and it's a resolution of 50,000 counts. This meter has a single temperature input. The real nice feature with this meter that these don't have is it can measure inductance to some degree. It didn't do a very good job of it. If we look at how these meters fared in my robustness testing, this DT9939 failed at 2.5 kV. The Bryman passed all the way up to 5.9 kV on the big transient generator, and unfortunately at the time I ran this I didn't have a way to step it on the small transient generator, so the next step up, which I think might have been like 12 kV or something, this meter failed. Of course the Unity 181A failed the one hit of the grill starter, and it took out the switch mode power supply chip in it. And of course the TPI failed when I had the rectified 220 volt AC connected to the input and I rotated the knob through the different settings. So the TPI didn't even make it to the ESD test, so by far the Bryman is the most robust of the 4 meters. This is model M248B. This is a 310,000 count meter. It's rated for Cat 4 300 volts. So go get your popcorn, get comfortable, and we'll see how this Gossen Metrawatt fares against the other 4 meters shown here. The Gossen meter arrived. The shipping box looked fine. Let's go ahead and open it up. See, it has a calibration mark of 2017-02. Temperature that it was calibrated at, and the humidity. Looks like everything checked out okay. Oh, it's just the documentation for it. Looks like a quick start manual for it. Comes with a couple of batteries. Industrial type Duracells. Probes feel pretty nice. I like this. Nice little detail. Leads are fairly long. It's interesting that the rubber boot is not installed on the meter. I think this is the first meter I've seen where it's actually got a metal hanger. I don't know if you can tell, but there's actually a metal insert that's been molded into the stand. See this? Like that's not going to bend. Huh. It's a pretty unique design. There you go. So the Metrahit Ultra, this one has the Bluetooth interface. It's interesting that the knob has two tick marks depending on what you're measuring. So it has two separate covers on the back, one for the batteries, the other one for the fuse. I wonder if they mark these so they know that it's got the original fuse in it. I've never blown one of these large fuses yet. See if you can hear this relay click. I think before we do anything with this meter, let's just give it a real basic checkout. Some time ago somebody was asking about the thermocouple input on the BM235. One of the things they had asked about was the temperature range of it. So what I had done is actually hooked up a thermocouple to the meter, and I increased the actual temperature up to the point where the meter overranged. So originally this box actually had a K-type thermocouple sitting inside of the case. What I've done is I've used the 5-volt reference that's built into this box, and I just have a divider network in here now off of that, so I can simulate a thermocouple. So on the low side I can put out 24 degrees up to about 1040. So if I take the BM235 for example, and we put this into the temperature mode, and if I set our pot up here to roughly the center point, this will be about 500 degrees C, and I'll just turn this on, and you can see it overranges the meter. So let's just adjust this down, so somewhere right around there. So about 450 degrees C is where it overranges. You can see right now it's just set at 428 degrees C. What I'll do, without readjusting the box, we can connect this to channel 1 of the BM869S, and you can see we're reading 426.6, and if I want to take this on up, so this is turned up all the way, so I've got 1035.5 degrees C of range. So this is going to be a lot more useful for testing the thermocouple inputs of the meters. The only thing I've been playing around with recently is different shunts. So this is a separate powered shunt that I came up with. This one happens to be fuse protected with a couple of back-to-back diodes. But one of the things that I thought I would add to this box is the ability to output a current. So again, all I've done is I've taken the 5-volt reference and I've installed some precision resistors and just divide this out. And there's going to be some error with this because you'll have to deal with the input impedance of the meter, but let's just have a look. So this will be the 100 microamp setting, so you can see it's reading 0.98 milliamps. So let's just go to the microamp range, and you can see it's 99.83 microamps. Next setting down is 10 microamps, and then 1 microamp, and then our last setting we can put out 100 nanoamps. Again, it just makes the box a little bit more useful for the testing that I do. Let's just go ahead and we'll start with our capacitance measurement. We can zero this thing out, maybe. So this first will be 150 picofarads. Let's try it with a 1 nanofarad. Looks real good. This will be a 0.1 microfarad. Looks real good. This will be a 1 microfarad. Let's try a 10 microfarad. Looks good. And this will be 100 microfarads. Real good. So that I'm pretty impressed with. Let's try the temperature input. So again, this should be roughly 500 degrees C or so. Let's just see how the continuity test works. Backlight looks pretty decent with it. It looks fairly even. Let's have a look at the viewing angle of the two. It's not too bad, really. I like the backlight on the Bryman. It's definitely a lot brighter. You can see it's not too bad. Again, this is with an open. Let's just see about the auto range. Takes it quite a while. What did the spec sheet say on this? Like 8 seconds? I could believe it. Let's just try the same thing with the BM869S. That's it. You can just see it's much faster than the Gossen. Look at this. You're going to be waiting a long time for this meter to settle out. Let's go ahead and we'll clear out our leads. This is with a 0.5 ohm resistor. This is with a 1 ohm 1%. This is with a 50 ohm 0.01%. This is 100 ohms 0.01%. Let's just try turning off the rail. It's a little high. I would expect it would read a little high down here as well at 50 ohms. Not too bad though. This will be a 1K 0.1%. Looks good, real good. This is a 10K ohm 1%. This will be a 100K 0.1%. This is a 1 meg 1%. And this is a 10 meg 0.1%. And unfortunately, again, the meter has no conductance. So this is a 100 mega ohm resistor, and of course it won't be able to read that. Did not try the diode mode. Let's go ahead and give that a try. It'll take some getting used to having the lettering on both sides of the dial. So this will be a single diode. That's fine. And here's 2. Looks good. And 3. Of course, the open circuit voltage on this I think is 4 volts. So this would be roughly 20%. Looks fine. So let's go ahead and we'll increase our frequency. So this is 200 kilohertz, and you can see it's reading dead on. So this is with 1 megahertz being applied. You can see it's having no trouble with that. It basically reads dead on. Let's just see if we can go up any higher. So there's 1.1. Oh, right there it overranges. So yeah, this is pretty much the upper limit of it. It'll just overrange regardless. Unfortunately, the hardware could probably read up a little higher. Looks like the software locks it out. So currently I have all 5 of these meters connected in parallel and attached to my fluke reference. And you can see I'm supplying 10 volts right now. So if you follow my channel, you know that the main control chip on this TPI 194.2 has been damaged. So it has a little bit of leakage current depending on what mode you run it in. But it'll be fine for these voltage tests. And of course the Bryman BM869 was also damaged and I had repaired it. The 181A I actually damaged the power supply controller chip on, and of course I replaced that, but then I chopped up the circuit board on this meter to improve its robustness. And of course the DT9939 was also damaged. So all these meters except for the Gossen have been apart. So just keep that in mind as we're kind of going through this. But you can see all the meters are basically reading 10 volts. Let's go ahead and we'll try them out at 1 volt. And I'll program it up for 1 millivolt. And let's just change them all to their millivolt range. And again, with the Gossen, you have to change this to the manual ranging mode to gain that extra digit. So what's going on with this? Do you see that? Huh. Look at that thing wiggle. What the heck is going on there? Look at that. Huh. Well, I wonder if there's not a problem with that meter. So again, I have all 5 meters attached in parallel and they're connected up to my function generator. So I don't know why, but it looks like the Gossen reads a little high. You can see we're up at 1 kilohertz right now. What I'll do is just set this to 1 volt. Let's just see what the 3 dB point is. I believe on this one it's actually quite high. It does have a filter function. So if we go to function, there you can see it's showing filter. So again, the data sheet, this is a 1 kilohertz low pass filter, and you can see it's very close to the 3 dB point now of the meter. So we'll just turn that filter back off. And we'll go ahead and adjust the frequency on up, and let's see what the actual 3 dB point is. You can see we are at 12 kilohertz right now, and this is pretty much the limit of our SEM meter. This is currently at 100 kilohertz. You can see the meter is still quite accurate. It's starting to peak up. So again, this is 320 kilohertz. You can see we are at 300 kilohertz. So yeah, I'm not sure what happens with it. It's like it freaks out when you go up a little bit over 300 kilohertz. Of course, the Bryman's not having any trouble with this. The Unity is starting to fade out just a little bit. Of course, the TPI is really starting to peak up. Here we can see this is the AC plus DC value. Of course, I don't have any offset right now, But you can tell on the TPI we have the DC content here, the AC and the AC plus DC. On the Bryman I get the AC plus DC and then the AC in the upper right. On the Gossen you basically only get the AC plus DC. The only way to get the other values is you actually have to switch between them. So here's your DC and your AC value. To me, this thing has a tri-display. It's a shame that you can't actually select between these. You know, if I go to function, I'll get the frequency, and then in the upper right will be the AC plus DC, but that's really all you can do with it. Of course, on the Unity 181A, it separates out all three values. In our little SEM meter, you can see it just reads the AC plus DC, and then I get the frequency in the upper right. Very similar to what the Gossen is showing us. So let's go ahead and we'll add some DC offset to this. So now you can see I have a 1 volt AC sine wave riding on top of a 2 volt DC bias. And you can see the AC plus DC on all the meters is reading roughly the same value. You can see the TPI, the Bryman, and the Unity are all reading roughly the same value. The SEM meter reads a little bit higher, and then we have the Gossen, which is reading quite a bit higher. So this is with a square wave being applied, and you can see all 5 meters are reading roughly the same value. Unfortunately, the Metrahit does not have a bar graph function. Of course, the meters that I've looked at so far, this Unity and this Bryman have the fastest bar graphs of all the meters I've looked at. This TPI is really bad, and so is the SEM. These basically update the bar graph at the same rate that the display is updated. So currently I have all 5 meters connected together in series. You can see I have the amp mode selected on all of them. And these are connected up to my bench power supply. Let's go ahead and increase the current a little bit. This is roughly 1 amp. You can see all the meters reading roughly the same value. And you can see the Bryman does not have the 500,000 count mode in the amps range. So it's kind of cool, it can read out that extra place. Let's go ahead and we'll increase it a little further. This is roughly 4.67 or so amps. See, all the meters are reading roughly the same value. We can go up a little bit higher with this power supply. This is with the power supply maxed out, so roughly 7.2 amps. Again, this is with all the meters in series, and I have them connected to a different bench power supply. You can see we're putting out roughly 185 milliamps right now. So the burden voltage on the SEM meter is about 1.2 volts. The burden voltage on the Unity is 235 millivolts. The burden voltage of the Gossen is 114 millivolts. That, I think, is going to be our winner. 326 millivolts on the Bryman, and 270 millivolts on the TPI. So with roughly 16 milliamps applied, again, it looks like all the meters are reading roughly the same value. This is using our little test box. Again, this is just a series resistor, and of course we have the series resistance of all these meters to contend with. This will be roughly 100 microamps. And this is with 10 microamps. And this will be 1 microamp. And this is with 100 nanoamps. So let's have a look at the burden voltage in the microamp range. You can see I'm applying roughly 2 milliamps right now. So our SEM is dropping 1.17 volts. The Unity, 108 millivolts. The Gossen, 120 millivolts. The Bryman, 230 millivolts. And our TPI is 233 millivolts. So it looks like for the lower currents, This UT181 actually has the least burden voltage of all the meters, but not by much. Again, 120 versus 108. It's not much difference between these two. So I think that's going to be it for this first part. Stay tuned and we'll have a look at this quirk that I'm seeing with this Metrahit. Notice as I kind of wave my hand in front of it, see how it's affecting the display. So let's see if we can figure out if this meter is actually defective right from the factory, or is this a possible design flaw with the meter? Stay tuned.